Most people think quantum mechanics tells us the universe is fundamentally random, that particles don't have positions until you look, that nature at its deepest level rolls dice. I want to challenge that. Not because quantum mechanics is wrong, it isn't. It's the most precisely verified theory in the history of science. But there's a difference between a theory that works and a theory that explains. And for nearly a century, we've been confusing the two. My name is Paul Dirac, and today we're going to talk about an idea that was voted down at the most important physics conference of the 20th century, and might have been right all along. It's called pilot wave theory. Let's start with what you were probably taught, the Copenhagen interpretation. An electron is fired at a barrier with two slits. Before it hits the detector, it has no definite position. It exists as a wave, a probability wave, spread across space, going through both slits simultaneously, interfering with itself. The moment you detect it, the wave collapses. The electron is suddenly somewhere, definite, real. This is the standard story, and it works. The math is clean, the predictions are perfect. But ask a Copenhagen physicist, what is the collapse? What physically happens when measurement occurs? Why does observation change reality? You'll get one of two answers. Either an elaborate philosophical framework that raises more questions than it answers, or a quiet, slightly irritated, "Don't ask that, just calculate." That answer always bothered me. In 1927, at the Solvay Conference in Brussels, the greatest gathering of physicists ever assembled, a young French physicist named Louis de Broglie stood up and proposed something different. What if the particle always has a definite position? What if we just don't know it? What if there's a real physical wave moving through space that guides the particle, the way a wave on water guides a cork? The particle surfs the wave. It's always somewhere. It's always real. We just haven't looked yet. He called it the pilot wave. Einstein, sitting in the front row, nodded. He'd been saying something like this for years, that quantum mechanics felt incomplete, that God doesn't play dice. Pauli stood up and objected. Heisenberg was dismissive. The vote, informal but decisive, went against de Broglie. He sat down, and for 25 years he didn't speak about it again. The idea didn't die, it went underground. In 1952, a physicist named David Bohm, working in Brazil, isolated, under political persecution, picked up de Broglie's broken idea and rebuilt it from scratch. He kept two things real, the particle and the wave, both physical, both always existing. The wave, described perfectly by Schrödinger's equation, the same equation everyone already uses, moves through space and guides the particle along a precise trajectory. The particle always has a position, always has a velocity. There's no randomness in the underlying physics, only in our ignorance of the exact starting conditions. Here's what made Bohm's results so devastating and so easy to ignore. It produces exactly the same experimental predictions as standard quantum mechanics, every single one. You cannot build an experiment to tell them apart. So physics had two complete descriptions of quantum reality. One that said randomness is fundamental, particles have no positions, and measurement is mysterious, and one that said particles always have positions, waves guide them deterministically, and measurement is just interaction, nothing mysterious at all. and physics chose the mysterious one. Let me show you why the pilot wave picture is so compelling. That double slit experiment. In Copenhagen, the electron goes through both slits as a wave, interferes with itself, collapses at the detector. Elegant, but strange. The electron is in two places, until it isn't. In pilot wave, the particle goes through one slit, only one, left or right, determined by its exact starting position, which we don't know. But the wave goes through both slits. The wave interferes with itself, exactly as Schrödinger's equation predicts, and that interference pattern in the wave steers the particle, pushes it away from certain regions, pulls it toward others. Fire 1,000,000 electrons, one at a time. Each one goes through a single slit. Each one lands at a precise spot. But because their starting positions are slightly different each time, and we don't know those positions, the landing spots look random. They build up slowly into the interference pattern. No collapse, no mystery, just a wave doing what waves do, and a particle following it. The randomness isn't in nature, it's in us. Now, what is this wave actually? This is where Bohm was brutally honest. He didn't dress it up. For a single particle, the pilot wave lives in ordinary three-dimensional space. Fine, intuitive. But for two particles, the wave lives in a six-dimensional configuration space. For three particles, 9 dimensions. For an entire system of particles, the wave lives in a space with as many dimensions as there are degrees of freedom in the universe. That's not a metaphor, that's the mathematics. So when people say pilot wave theory is more classical than Copenhagen, be careful. The particle is classical, definite position, definite velocity. But the wave is not classical at all. It's a structure of almost incomprehensible complexity, living in a space we can't visualize, encoding the entire state of everything. Bohm knew this. He didn't hide it. He thought it was telling us something, that reality has layers we haven't begun to understand. There's a price for all this determinism, a heavy one. The pilot wave is non-local. Here's what that means. In an entanglement experiment, two particles, separated by any distance, the pilot wave connects them. Not as a metaphor, physically. Change what you do to one particle, and the wave adjusts everywhere, instantaneously. John Bell proved in 1964 that any hidden variable theory, any theory where particles have definite properties before measurement, must be non-local. There's no way around it. Pilot wave theory accepts this completely. The wave doesn't respect distance. It's one global object, and it responds to the whole experimental arrangement at once. This doesn't let you send signals faster than light. The non-locality is real, but it's hidden beneath a layer of statistical noise that prevents you from using it. Relativity is safe, technically, but the universe it describes is deeply, fundamentally interconnected. Bohm spent the rest of his life exploring what that means. He called it the implicate order, the idea that what we see as separate objects are really folds in a single underlying wholeness. That's not physics anymore, some would say. Maybe. Or maybe it's where physics has always been heading. So why did the physics community reject this? Not because it made wrong predictions. It doesn't. Not because it's mathematically inconsistent. It isn't. The rejection was aesthetic, social, historical. By 1952, the Copenhagen interpretation had been dominant for 25 years. Careers were built on it, textbooks written. The randomness of quantum mechanics had become almost a point of pride. Nature is fundamentally uncertain, and we've accepted it, and you should too. Bohm's theory felt like a step backward, too deterministic, too classical. It brought back the ghost of a universe running on hidden clockwork, and the establishment didn't want that ghost. There was also the politics. Bohm was called before the House Un-American Activities Committee during McCarthyism. He refused to testify. Princeton fired him. He was forced to leave the United States. He spent years in Brazil, then Israel, then England, brilliant, productive, and mostly ignored by the field he'd contributed to. His theory was buried under a pile of dismissal that had very little to do with its scientific merit. I want to be honest about where pilot wave theory struggles. Non-relativistic quantum mechanics, single particles, simple systems, it handles beautifully. But quantum field theory is different. In quantum field theory, particles are created and destroyed. They're excitations of fields. Extending the pilot wave picture to this domain is genuinely unresolved. There are proposals, there is progress, but there is no clean, complete, universally accepted formulation. This is a real limitation. Anyone who tells you pilot wave theory is the finished answer to quantum foundations is overclaiming. But here's the thing. Copenhagen doesn't explain collapse either. Many worlds multiplies unobservable universes without limit. Every interpretation of quantum mechanics has unresolved problems. Pilot waves problems are different, not uniquely damning. The question isn't which interpretation is perfect. The question is which one is pointing at something real. If pilot wave theory is even partially right, the implications reach far beyond physics. It means quantum randomness is not fundamental. It's epistemic, a reflection of our ignorance, not of nature's indeterminacy. The universe runs on laws we haven't fully accessed. Determinism isn't dead, it's hidden. It means Einstein's discomfort with quantum mechanics wasn't the stubbornness of an old man clinging to classical intuition. It was the instinct of someone who sensed that a theory can be empirically complete and conceptually incomplete at the same time, that working and explaining are not the same thing. It means that for 70 years, the dominant interpretation of our deepest theory of nature has been, possibly, a placeholder, a calculational tool dressed up as a philosophy. And it means the question de Broglie asked in 1927, and Bohm resurrected in 1952, and a small community of physicists has been pursuing ever since, is there something underneath, is still open, still alive, still waiting. The electron always knew where it was going. We just didn't ask the right question.